All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. Had some technical difficulties there, but we were in the middle of examples last time. Let's get started. Okay, there we go. All right, screen up and running. Let's do this. All right. Where's my stuff? Okay, so we had one more counting example to finish. We're going to do that. Then we're going to talk about, I wanted to talk about some other ways to visualize stuff. As you've seen, we've been doing with counting. So sometimes you know that, oh, I'll do like these slots and things like that sort, which we actually use pretty often with these guys. But there are other ways to visualize things. I want you guys to know how to do that because every now and then it'll help with our counting. So we're going to do that, and then we'll actually start talking about probability. We won't get farther than some definitions today, but we will continue. Let's actually jump into this. Okay, so we have 10 balls labeled 1 through 10. Put them in a box, we shake them up. We pick 5 at random. After each pick, you do not replace the ball, and then you pick again, right? So this is called sampling without replacement. How many possible scenarios are there of this kind? And the kinds are described here. So A, the second of the 5 numbers is an 8. So how many ways can you do this so that the second ball that you draw has an 8 written on it, right? And in part B, the second of the 5 numbers drawn is larger than the first number drawn. Okay, so let's actually do that. So, okay. Okay, so again, what we'll do here is we'll kind of visualize things. Obviously, what we want here is that we're drawing 5. 1, 2, 3, 4, 5. And we want the second number to be an 8. Right? So how many choices do I have for the other positions?
Would it be 9 choices?
You'd have 9 choices. Remember, again, choices in blue. Numbers in blue are choices. And what else? What about the number over here? This guy. How many choices for the third number? Choices for the third number? Well, the sampling is without replacement, which means that once I've chosen one of the 9 choices to put in the first slot, I now have 8 choices left for the third slot, and so on. So turns out by the multiplication rule, we have 9 times 8 times 7 times 6 equals, I believe that's 30, 24 total choices. You can also note, alternatively, you could think of it as we make, or let me do it another way. A choice is made for us. For the second number, we now need to choose from 9 other numbers without replacement. Another way to say that means no repetition. And put them in order, right? So I'm going to choose something for the first number, the third number, the fourth number, and the fifth number, right? I'm doing things in order. I'm not allowed to pick anything that was picked before, which means repeats aren't allowed. So what does that remind you of? Well, it's a permutation. P of 9 choose 4. I had to choose 4 numbers from the remaining 9. That happens to be, right, 9 times 8 times 7 times 6.
Professor, can I just add something?
You're breaking up. I can't hear you.
Can you hear me?
No, you're still kind of. I don't know if you want to type something, but your mic seems to be messed up. B, the second of the 5 numbers is larger than the first number. That one is a little bit more tricky, which I will go through and sort of show you. So we can get on our way here. So what are the options for the second number to be larger than the first? Well, one thing you can note is that 1 could not be the second number. So that's the first thing. 1, 2, 3, 4, 5. 1 can't be the second number. Right? Because 1 would not be larger than the next number if the second number is 1. So it means that our options then is that the second number has to be 2 or bigger. Oh, here's the question in the chat. Question is sampling without replacement. If we have 9 choices for the first spot and we draw 8 on the second spot, why do we have 8 choices left again for the third spot? No, so this here, this actually counts as 1 choice here. Right, so the 8 in quotations is not the choice that I'm counting. The 8 is actually One choice was made for us, and it was the number 8. So because there were 10 numbers, which means once someone chose the number 8 specifically and put it in the second slot, we now have 9 other numbers over here that we need to pick from. I can pick any of those 9 to put in the first slot. I can now have only 8 of them to put in the third slot, then 7 of them to put in the fourth slot, 6 of them to put in the possibilities for the fifth slot. Right? So I mentioned here the numbers in blue are the choices. The 8 here that's written in white is not the choice. It's actually the name. It's actually the name written. It represents one choice. It's a choice that was made for us. Yeah. So the 8 here in quotations and the 8 here aren't the same thing. One is representing choices. One is representing the actual thing that's written on the ball. Okay. So, all right. Which means it's possible that I have a 2 in the second position. In which case, how many things could I put in the first position if I know that the second must be larger than the first? Well, I would only have one choice for the first position, namely the number 1, right? So 2 is in the second position. It has to be 1 in the first position. And so now I would have to choose how many left. Well, there will be 8 choices left to pick, right? So there's 8, 7, 6. Right? So that would be, 8 times 7 times 6. Now, you can say, well, it doesn't have to be a 2 in that position. Could be a 3. Now, how much would it be if there were a 3? Well, with the 3, there could be 2 possible choices I could put here, either a 1 or a 2. So after the 3 is chosen, and then I've made one of 2 choices there, now 2 numbers would have been filled in, and I have 8 choices left. And we keep going. 1, 2, 3, 4, 5. I could have a 4 here, or I could have a 5 here. 1, 2, 3, 4, 5. Or I could have a 6 here. 1, 2, 3, 4, 5. Or I could have a 7 here. 1, 2, 3, 4, 5. Or I could have an 8 here. 1, 2, 3, 4, 5. Or I can have a 9 here. 1, 2, 3, 4, 5. Or I can have a 10 here. Right? So the idea is once the first 2 are chosen, once first 2 chosen, eight numbers left to sample from. Okay. Now, if there's a 4 in the second position, there are 3 possibilities of what to put in front of it to make sure that the 4 is larger than those things. But once we've made those 2 choices, I now have 8, 7, 6 choices left. If there's a 5 in the second position, I have 4 choices for what to put here. I can put a 1, a 2, a 3, or a 4. Once I've made those 2 choices, I put the 5 and one of those that I just mentioned. I will have 8, 7, 6 choices left. Similarly, it's 5, 6, 7, 8, 9. And in all these cases, I would have 8, 7, 6 choices left. So over here, this would be, well, I would have 2 times 8 times 7 times 6. Here, I would have 3 times 8 times 7 times 6, and so on. Then here, now I want to add them. Since no overlap. So what would I have? You'll notice that there's a common 8, 7, 6 there. So I would have like 1 times 8 times 7 times 6 plus 2 times 8 times 7 times 6 plus 3 times 8 times 7 times 6 plus dot, 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 all the way up to 9 times 8 times 7 times 6. Right? Now, even if you have a calculator, that's kind of annoying to actually plug in. So what we would do is we notice that, oh, the 8 times 7 times 6, that's a common term. I would be able to factor that out. Let's 8 times 7 times 6, that's what's factored out here. iPad is still misbehaving. Ugh. Okay. I was giving trouble earlier too, that's why we started so late, but yeah. So I guess we'll just hang out here for a while. How are you guys doing? I'm kidding. Yeah. Let me just get this going. Should have like an intermission thing. If I was a great video editor, I would put like some elevator music here. You know that scene in Avengers where Captain America is like taking the elevator? Okay. The elevator wasn't worthy. All right, let's see. We are back. Let's see here. I think every time I turn this thing on, I have to repair this thing. Okay, I think we're back now. All right, so here I would factor out. Notice that what we would have over here is 1 plus 2 plus 3 plus dot, 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 all the way up to 9. We actually had a formula for that. The sum of the first 9 positive integers. Remember I told you that story about, oh, baby Gauss, how he added up numbers from 1 to 1,000 when we're deriving that formula. So yeah, we actually know a shortcut for this. This is actually going to be 9 times 9 plus 1 all over 2. I mean, you could add these all up in your calculator as well, but it's actually easier to just know that formula. So then you can be like, well, you know, 2 goes into 8 4 times, and so the answer is really going to be 4 times 7 times 6 times 9 times 10, and that's going to be 15, 120. So that's how many ways to actually choose the 5 numbers without replacement in such a way that the second number is larger than the first. You would not want to have to list all of those, but now, because we know how to count, it's not that bad. All right. What I want to do now, so that's that. So we did that whole slots thing, that whole idea, but there are other ways to visualize things that I want us to be aware of. Other ways. I just feel like this thing is too thin. It's going to seem too thick by comparison now. Other ways to visualize processes. Yeah, I think that's probably a good way to phrase it. So let's actually talk about that. Other ways that we can visualize things. So I showed you that thing about the dice. I showed you the slots thing, but there are some other common ways to do things as well. Tables and tree diagrams. Let's talk about, to illustrate both, we'll go back to the example of flipping a fair coin 3 times. And figuring out the probability of 2 showing heads. So this was on the probability teasers. We actually remember, hopefully you remember, the answer was like 3 out of 8, right? So let's actually figure that out. So we figured out it was 3 out of 8 because we knew the multiplication rule. So we knew that there were 2 choices in each slot. So let's do it that way. Before, what we did was, okay, toss 1, toss 2, toss 3. And we knew that there were 2 choices, 2 choices, 2 choices. So that led to 2 cubed equals 8 total choices. If heads is in 2 positions, this means tail is in 1 position. There are 3 positions possible for the T. Hence, the probability is 3 out of 8. There are 3 ways out of 8 that you could get this, right? So we sort of did that reasoning last time. I want to actually do it another way. Now, let's do it other ways. Let's do this problem in other ways. Because sometimes there are more than one way to skin a cat. Certain procedures might jive well better with some people than with others. So I don't just want you to know one way to do these guys. I want you to know several ways to visualize things, several ways to think about them, several ways to do them. So let's start out with tables. So I want to tell you how to generally construct tables in the situation that we know we have Because I had a way of phrasing this. Okay, so suppose we had a process with R stages, and each stage has n possible outcomes, the same n outcomes for each stage. Then one can visualize all possible outcomes by alternating them in a table as described below. So dot, dot, dot. So you're going to have a bunch of rows. And here's how you're going to do this. You're going to alternate every blank rows. So in the first column, which will go from the right, just for traditional reasons, actually, every n to the 0 rows, then every n to the 1 rows, then every n to the 2 rows, and you keep going to every n to the r minus 1 rows. There will be, in this case, r columns, and you will have, and the number of rows would be n to the r, which is equal to the total number of possibilities. By the multiplication rule. So that's in theory how you could construct this table. Let's get to this particular example. For this example, we have R equals 3 stages, namely coin tosses. And we have n equals 2 possible outcomes, namely heads or tails. So how can you construct a table to make sure that you are actually seeing every possibility? So what we will do here then is there will be a table with 3. There will be a table with 3 columns and 8 rows. right? So 1, 2, 3, 4. That one's all of it. 4, 5, 6. Come on, iPad. 7, 8. And now here, so let this represent, say, toss 1, toss 2, toss 3. Now you're going to alternate every blank rows. Here you're going to alternate every 2 to the 0 rows. Here you're going to alternate every 2 to the 1 row. Here you're going to alternate every 2 to the 2 row, right? So in the first column, you're going to alternate every other row. 2 to the 0 equals 1, right? You're going to alternate every other row. So I'm just going to go through and fill this out. Heads, tails, heads, tails, heads, tails, heads, tails. Alternate every other row. In the second column from the right, I'm going to alternate every 2 to the 1 rows, every 2 rows. So I go heads, heads, tails, tails, heads, heads, tails, tails, right? Alternate every 2. In the third column, I'm going to alternate every 2 squared rows, every 4. Alternate every 4. 1, 2, 3, 4, 1, 2, 3, 4, and so on. Now, this table, as written up this way, represents all possibilities. I don't need to worry about, oh, did I forget some order of the, well, what if the 8 came second in no, maybe, wait, did I already do all the places where the 8 came second? Like, no, this is everything, right? Once you follow this pattern of filling out the table, you have all possibilities. Make sure the number of rows follow the multiplication rule and fill out the table in this way. You will have all possibilities, and it's represented here. I can get a heads first, heads second, heads third, or head first and second, but a tails third, heads then a tails then a head, or a head then a tail then a tail, then a tail then a head then a head, or a tail then a head then a tail, or a tail then a tail then a head, or all 3 tails, right? This is all possibilities, and I can actually see all possibilities right here. I can tell you specifically what's going to happen. And now, if you were to ask me, so now you see that there are 8 totals. Possible outcomes for the 3 toss experiment. So now I know that the denominator of my probability is 8. Now to figure out the numerator, what do? Well, we want 2 heads to be the thing that we want. So what I do is I would just go through all these rows and pick out all the rows with 2 heads. So here I have 2 H's. Here I have 2 H's. Here I have 2 H's. That's it. There are only 3 situations. So there are 3 possibilities with 2 heads, right? So this means the probability of 2 heads well, that's going to equal 3 out of 8. Okay, and I can do that from figuring out the table. Another thing that we can do, so that's how you would figure it out from a table. Let's see here. Talk about tree diagrams. another way to visualize the process. Many kinds of processes, but I'm illustrating with this particular example. So here's how you'd set up the tree diagram. So there's going to be, say, stage 1, stage 2, stage 3, right? Which is, of course, toss 1, toss 2, toss 3. Think of these guys as they're just some columns. Kind of imaginary. You don't even really have to draw these blue lines. And over here is time before experiment. And you can draw a point here, and it's like experiment starts here. And then what you would do is you'd write out all possibilities. So at the start of the experiment in stage 1, how many ways could that happen? Well, it could happen in one of 2 ways, Captain. It can go heads or it can go tails. And now stage 2 has 2 possible starting points. And you're like, what can we do now? Well, I could again go heads or tails. Similar for this one. Now what for the third stage? I can go heads or tails. You'll notice here that there ends up being, let's be consistent here, 8 possible ways the experiment can end. Right? And so the thing with the tree diagram, what you can realize is that each arm represents a possible outcome. Each arm represents a possible outcome. And by the way, multiplying the probabilities across each arm gives the probability of that outcome. I'll tell you more on that later, kind of jumping ahead here. And second thing you should know, yeah, so I mean, each node, that's the dots represent possible starting points for the stage of an experiment, possible starting points. For a stage of the experiment. Okay. And now again, so going along each arm can give me a possibility. So how many ways can I get, say, 2 heads? I can get a head and then a tail, because I won't choose that. Or I can get a head and a tail and a head. Or I can go a tail and then a head and then a head. you'll notice that there are 3 arms that give us what we want. Here, 3 out of 8 arms give us what we want. Right, so that's kind of like a tree diagram. It's another way to visualize things, very common, especially when you don't have not a lot of things to count. I mean, 8 things isn't that much. Same thing with a table, right? A table with 8 rows isn't that crazy. But these are just alternatives on how to visualize things. So you can do it the slots way and count with the multiplication rule and figure out, well, how many ways can I fill out each slot? You can also fill out a table. All the possibilities will be staring you in the face. You can get very specific very quickly. It will be a little more writing to do though. Tree diagram, same thing. Yeah. Now, hopefully that was clear. An important fact to recall. I say that, but I feel like I forgot to actually mention this to one of the classes, and I forgot which one I forgot to mention it to. But I was going to remind you of it either way. So this might be the first time I'm saying this. I don't know. But we can define a notion called disjointness. We say A and B are disjoint if they do not intersect. The intersection is the empty set. So it's like if you have a Venn diagram, your A and your B would be completely separate. A is over here, B is over there. They don't overlap at all, right? When we have 2 sets that don't overlap, they share nothing in common. We say they are disjoint, quote unquote. It's going to be very important, not for this class, because it actually took a lot longer than I expected to get here, but it'll be important for the next class. So now let's not push it. Star probability next class. We'll start with a vengeance. We will move a little bit faster. But yeah, all of this, the counting is going to be very important. How to visualize things is going to be very important. Really knowing when to use combinations and permutations will be very important. You're going to have to determine, does order matter? Does order not matter? Do repeats? Am I allowed to repeat stuff? Am I not allowed to repeat stuff? All of these things put together, I would say take another couple days to really kind of have these things sink into your mind. Because if we move forward without you really having all that under control, probably is going to seem very hard. And it's hard anyway. And I'm going to explain to you why it's hard later on. But for basic probability like we'll be doing, it doesn't have to be hard. As long as you have certain principles in your mind, which is why I'm taking a very long time to actually build these guys up, you'll realize that it's more or less straightforward. However, why we especially need to study something like probability is that there are times when probability will defy our intuitions. So there are times when we need to know about probabilities in the real world, but our intuition is going to tell us something different from what the actual answer is. And we'll deal with cases like that when we get to it. We already kind of did with the probability teasers when I was asking you guys about those probabilities and you're like, I don't know where that number even comes from. But there are times when you'd actually have an answer in your head and you're like, I know that's the answer. and you'll be wrong. Like you'll be just like, you'd have like this whole logic going and yeah, because of this and I blah, blah, blah. This is definitely, yeah, that's the answer. And you'll know that's the answer and it's not the answer, right? So that kind of makes probability kind of weird, but I'll tell you about those situations when they arise and what you would really do to overcome that. As long as you stay according to the process that I'm going to give you, you're going to be pretty much safe. So I'm going to build things up so you use formulas and you count things in terms of sets and things of that sort. Use certain formulas, use certain logic in certain situations, and you're going to be okay most of the time if you remember all these steps. But with that, I think we'll end there. That's that. And you met your coaches yesterday. I don't know if they reached out to you guys already, but yeah, it's going to be good. For now, we will stop there. We will be doing more counting. It's just that we'll be doing it in the context of probability next time. So with that being said, I will see you guys in the next one.